Welcome back to Introduction to Artificial Intelligence System. Today we're gonna keep learning the first topic of regression, and today, based on the last topic, we're gonna learn, especially for overfitting problem and linear basis function models, regularization and evaluations. Let's first talk about the topic of overfeeding. Overfeeding is kind of the production of an analysis that corresponds to too closely or too exactly to a particular set of data, so it may fail to fit the additional data or predict future observations. So let's see what this exactly means. So for this, let's first start with a linear regression problem. So in the last time we have learned how to model a regression model, especially for linear model for the given data. And as an extension of the linear regression, let's record nonlinear regression. In the last time, we have learned that nonlinear regression is basically just exactly the same as linear regression. So for that, we took an example of polynomial regression, and for this, we took a quadratic equation use as an example. And for that, we can see that the regression form has the nonlinearity. But the idea to convert this nonlinear regression to linear regression is that we constructed a nonlinear feature. So here, feature. So the nonlinearity is represented as a phi matrix, and by constructing this phi matrix, the final form of the regression problem is that just basically the same as y is equal to ax form. So the final form is just our objective of this nonlinear regression is finding proper X matrix or the variable of these zeta matrix. So by using the linear algebra, we were able to solve this nonlinear regression as a linear regression problem. And by keeping this in mind, we were able to represent more representative we were able to define a more representative matrix. So compared to a single linear equation that has the form of like only the first term of y is equal to ax plus b form, by considering more variables, we can represent more representative functions. So by using that, we were able to define model more accurately. However, in the case of when we increase the number of the term, when we keep increasing the number of terms, as you can see here, the problem becomes it's too representative, so it may cause the problem which is called an overfitting problem. So let's assume that we keep increasing the degrees of polynomial fitting with different degrees. So as you can see here, when the degree is too small, we don't have much degrees of freedom to represent this fitting function. So its accuracy is we cannot say its accuracy is high. And when we keep increasing the degrees, polynomial fitting with degrees, we can see for proper values for the 3 and 5, it's quite representative and its accuracy is quite good. But when the case is too high, then we have too much representative degrees of freedom, so that we can see that there are too much fluctuation here. So we can conclude that in this case, low error on input data points, but we can clearly see the high error nearby. That means at this point, the error is very small, but as you can see in the nearby points, very high error, so it's not a good case. Quantitative analysis, let's calculate a residual sum of squares. And when we keep increasing the, as we can see in the previous slide, when we keep increasing the degrees of polynomial, its residual sum of square becomes small. So in the case of 9 degrees, we can see very low error on input data points, but uh, we have seen that very high error at the nearby points. Then what kind of problem is this? It, in previous slides, we have seen that when we keep increasing the degrees of polynomial, then that means the low error of input data points, but it may cause high error at the nearby points. And by this sentence means we will have very low error on training data, but we'll have very high error on testing data. And when we think of the meaning of regression, the regression is kind of finding best fitting model for the data, so that we can use that model to predict for unseen data. So in this case, this point would be the unseen data, and this one is the data that we already have. So by finding this best fitted model with regression, our ultimate goal is to predict the values at this unseen data. But when we think of the overfitted problems, like when the degree is the polynomial function of degree is like 9, let's see, this point would be unseen data. And as we can see here, for the training data or data that we have, the error is very small. But in the case of unseen data, our prediction model will give the result of the predicted value like -11. But actually, this value, the truth value would be somewhere here or somewhere here. So it will cause very large error for this unseen data. So this may cause a very significant problem. So it is very important to determine proper values for the degrees to represent a proper represent data properly. So when the degree is too small, we call this as underfitting problem. So in this case, both error for trained data and test data is quite high. And in the case of proper degrees, and we can see that the error becomes small for both train and test data. However, if you keep increasing these degrees, for overfitting problem happens. So in this case, we will have very small errors for the training data, but we will have very high error at test data. So it is very important to select proper values of the degrees at polynomial regression, so that we can have properly represent our data and properly predict our new data. So that's the topic about the overfitting, and from now on we will discuss about the function approximation, which is also called a linear basis function model. Approximation is kind of selecting coefficient coefficient among a well-defined function, and we call this as a basis that closely matches a target function in a task-specific way. And this is actually exactly what we have done when we do in polynomial regression. Let's revisit the nonlinear regression that we have learned in the last time. So, as an example of nonlinear regression, we have learned the polynomial regression, and for that, we took an example of quadratic equation as an example. So, for the polynomial and nonlinear regression, our objective is finding the proper theta value for these quadratic equations. And for that, we first constructed this pi matrix, pi basis, and based on that, we constructed this pi matrix. So by using this, we were able to construct the matrix form, which is equal to y is, which is exactly the same as y is equal to ax form. So for that, A matrix is nothing but these bases, and the zeta x matrix is just our objective design parameter, which is just zeta value. So by constructing this y is equal to ax form, we were able to solve this theta based on the linear regression. So that's what we have learned in the last time, and based on that, we can think this problem differently. So here we can think that the problem is just exactly the same as approximating a target function as a linear combination of bases, which means from this part, what we have done is just exactly the same as finding finding best combination coefficients of this value. So by finding these by keeping this as a base, one of the bases, then our objective is finding a coefficients of these bases. So this matrix multiplication is nothing but the theta 0 b0 x plus theta 1 b1x plus theta 2 b2x. So our objective is finding the coefficients of these basis vector. So this problem is nothing but approximating a target function as a linear combination of bases. So in this quadratic equation, our basis can be regarded as like this. So the first basis is the 1, and the second basis is the x0 term, x first term, and the second and the third basis is x squared term. On this different perspective, we can also construct any explicit feature vectors with any nonlinearity. So for that, these two are the representative examples of fixed nonlinear functions. So So in the case of polynomial, as we have seen in the last slide, the nonlinear function, a fixed nonlinear function or fixed nonlinear feature vector was nothing but the term of the x0 term and x first term and x second term. And from now on, we will also see the regular basis function. Let's first think about the polynomial basis. As we have learned in the last time, the polynomial basis is just finding the coefficient for proper coefficient for y is equal to theta 0, theta 1x, theta 2x, 2x, the second term, something like this. And when you plot the basis function for this basis function for this polynomial, as you can see here, the basis would be like 1. The first basis is just 1, and the second one is just x, y is equal to x, and the third term is y is equal to squared x squared, so blah blah. So these are the polynomial bases. So and when we think of this polynomial regression as a function approximation term, then the meaning of regression is finding just proper coefficient for these bases. So for that, let's first let's say if you increase the theta 0, then the polynomial basis function would be changed like these or these. And if you change the values for theta 1, then this the slope of this y is equal to theta 1x. The slope will be changed, so it will be like more sharpened. Or if those coefficient if the coefficient is negative, then you will have negative slope. Oops. In this case, if you change this coefficient, then as you can see here, some value would be suddenly changed. So, and similarly, at this point, the values would be suddenly changed. So it will have very big difference at these near points. And the second case is RBF basis. And RBF is a radial basis function with bandwidth sigma and k RBF centers. So these are the expression for the RBF, and this one is very similar to normal distribution. And when you plot this RBF function, then RBF function has the form of like this. And similar to a normal distribution or Gaussian distribution, if you increase the bandwidth sigma, then you will have very spread function. And when you decrease this bandwidth, you will have very sharp distribution. And one of the main advantages of using a RVF function is this one is also just each one represent the basis for the RVF. So the coefficient for this one can be written as like this. And if you increase the coefficient of theta 3, then it will have the form of like this. And regardless of the coefficient of theta 3, as you can see here, the values at the other points does not show any big difference. So one of the main advantages of using RBF basis is it's highly localized. It's good to represent highly localized patterns in data. So the idea of implementing this linear regression with RBF using Python is exactly the same as what we have learned in the polynomial regression. So firstly, you need to define the basis function, and then you need to define the basis function and treat this as a matrix, and just solve linear algebra problems by using this relation. And if you keep increasing the degrees of RBF for many features, our prediction models become very expensive. But also, this is similar to polynomial regression problem. It can lead to overfitting problems. So if you have too much expressive functions with high degrees of RBF, here we also see that overfitting problem happen in this problem. Then how can you avoid, or how can you solve this overfitting problem? The idea is using a regularization. When we think of the reason why the overfitting problem happen is there is a fundamental problem. And the fundamental problem is that our objective function is optimizing parameters to solve this problem for data. And here y hat and yi is exactly the one that we have. But our real objective is actually finding proper model and minimizing the loss of prediction on new data of x and y. So this is also known as the generalization error. So do you know the difference between this one and this one? What we have done is actually optimizing parameters to minimize this problem, but our real objective is actually reducing the error for the new data or unseen data. So the way to avoid this overfitting problem is, let's divide data into training set and validation or testing data set. So let's say in this example, our objective is minimizing error for these data set. So as you can see here, our model is bestly fitted to minimize these error. But as you can see here, the unseen data set for these unseen data points, it will cause a very high prediction error for these points. So to avoid them, the problem solving is dividing data into two parts of training set and test data set. So let's say for these 10 points of data that we have, let's first divide some part. Like for this part, let's use for training. And for these points, let's use for testing. So by using only these training data set, let's make a regression model and let's test data for these unseen data set. So that's one way to avoid this generalization error. And the second way is to avoid this overfitting problem is choose less expressive function. So as the overfitting problem is resulted from the point that we have too many expressive and too representative model. So the way to avoid the overfitting problem is just choosing less representative function. So just reducing degree of a polynomial or fewer RBF center or a larger RBF bandwidth, etc. Let's implement this less basis function with fewer RBF center. So for that, let's select 4 cases of degree with 2, 4, 6, and 10 RBF centers. And this one, as you can see here, with less basis function, when the number of RBF is just exactly just 2, 4, and 6, and 10, we can see when we keep increasing the number of RBF centers, we can see the overfitting problem is happen. So the one way is to reducing the fewer RBF center to avoid this overfitting problem. The other way to avoid the overfitting problem is keeping the magnitude of the parameter small. And for this strategy, we call this as a regularization. So regularization is just penalizing a large parameter theta. So by implementing this regularization, our objective function becomes like minimizing the error between between these term plus lambda plus minimizing this large parameter theta also. So here the value between the lambda is called a regularization parameters, which is trade-off between low loss and small values of theta. So this one is our original loss function, and this one is to avoid the large parameter theta. So the lambda will balance will be the parameter balancing between low loss and small values of theta. Let's learn the regularization strategy in more detail. So often the overfitting problem is associated with a very large estimated parameters. So we want to balance between how well function fits data and between and magnitude of coefficient. And the first one is exactly the same as the loss function, that our original loss function. And the second term is penalizing the theta value. So the total cost or total loss function will become as measure of fit, which is just exactly the same as our original loss function without any regularization. And the second term is measure of magnitude of coefficient, which is exactly the same as norm or magnitude of the theta. So here we used the L2 norm for measuring the loss, and also L2 norm for measuring the magnitude of the theta value. And here the lambda is just the tuning parameter, so you should properly use a proper value for lambda. And in this case, we have two objectives. The first one is minimizing the error for the loss, and the second one is minimizing the magnitude of the theta. So we call this as a multi-objective optimization. The second term that we have introduced for the regularization is also called a shrinkage penalty, and is small when a theta are close to 0, and so it has the effect of shrinking the estimates of the theta towards 0. And the tuning parameter serves to control the relative impact of these two terms on the regression on the regression coefficient estimates. These two terms represent the loss, the original loss, and the second term is the magnitude of the zeta. And this problem is also known as rich regression. Let's see how these regularization works to avoid the overfitting problem. So for that, let's first start from a rich representation, which means we have too much expressive ways to represent the model, so it may cause overfitting problem. So for that, we first set the degrees of the number of the RVF function for 10, and these are exactly the same that we have the way we implemented for this RVF regression. And as you can see here, the results are the model is overfitted. And here we set exactly the same, but in this case we introduce an additional term for penalizing this the magnitude of the zeta value, so which is just regularizing coefficients for zeta. So before that, the old part is exactly the same, but here we implemented one additional term, which is minimizing the sum square of zeta. And here, and by using CVXY, let's solve this problem. And we can clearly see that model is the model is free from the overfitted problems. So the lead data is well representing the model, so it reduced the error for the unseen data, so it can overcome the overfitted problem. Then you may have questions on how this regularization works. And to do that, let's plot the coefficient of zeta value. And in our previous example for lead problem, where we have introduced additional term of regularization of reducing the magnitude of zeta, actually we have a total 10 values of zeta, right? Because we set the number of RVF function as 10. So that means, so when we plot the magnitude of each zeta value, we can see that the magnitude was relatively small. With the magnitude was relatively small, so that means for these part, they did not affect to the model well. So because of that, they did not affect to the model. So we have a less representative model that has very high magnitude of this zeta value. And of course, if you increase the value of lambda, which is the penalizing term, of course the value of weight becomes very small compared to the case without using this penalized term. In our previous example, we use L2 norm as a regularization term. So here our objective function was like this. So our objective is minimizing both error and also minimizing the magnitude of the coefficient. And for that, we implemented L2 norm for this penalizing term. And this problem is called a rich regression. And instead of using L2 norm, we can also use L1 norm. And for that, if you use L1 norm to measure the magnitude of the coefficient, this problem becomes lasso. So lasso is also least absolute shrinkage and selection operator. So the only difference is using L2 norm or L1 norm for measuring the magnitude coefficient. And the model result with RVF with the lasso, which means using L1 norm for measuring the magnitude of coefficients. We can also clearly see that the lasso regression model also represent the model data well, so it can be avoided from the overfitting problem. So this one is the approximated function or regression models look similar to that of Lich regression. And when you plot the coefficient data with lasso, then we can also clearly see that the magnitude of some value is very small. Some values are very small, and especially for some values, it has the zero values. Meaning of the coefficient with zero means the lasso has some features, has some properties of feature selection. That means least square with penalty on the L1 norm of the parameter. As a result, we see that the sum coefficient is exactly to zero value. And that means we knock out certain features. So that so the L1 penalty has the effect of forcing some of the coefficients estimates to be exactly equal to zero. So that means the problem of using the high degrees of freedom, which means using, for example, using large, using higher degree of polynomial or using many RVF function is may cause overfitting problem. But when you use lasso, then the result will make some coefficient to zero, and that means, for example, for the polynomial case, so zeta 2 x square, zeta 3 x, and by resulting some values, then you have not that much a representative function. So that's how to avoid the overfitting problem when you use lasso. So non-zero coefficient just indicate the selected feature. So by selecting some of the coefficients, then we have function that represent a proper number of the representative bases. So by using some of the selected bases, we will we are now good at representing our model, our data, and overfitted, free from the overfitted problems. So, of course, when you plot the result with the regression with selected feature, we can clearly see the result is. The reason why the only lasso has some selected feature property is you can see, you can find the reason from the geometrical point of view. So let's say this one is the the red plot represent, let's say the red plot represent the minimizing function for our original loss, and by having this L1 norm or L2 norm, we have a constraints which are subjected to L1 has very small value of S1 or S2. Of course, similar to this lambda value, S1 and S2 is just a user-defined values. So yeah, user-defined value. And when you represent this optimization problem in geometrical point of view, this one is the case for lasso. This one is the case for leech. And the difference between the lasso and leech is using L1 norm or L2 norm for measuring the magnitude of the theta value. And for the theta value of the L1 norm, we can expect the use of the diamond shape, which is exactly the same as like this. And in the case of a leech or L2 value, the magnitude is represented as the radius of the circle. So leech is represented as a circle, and lasso is represented as a diamond. And here, to satisfy these constraints, we need to find the values that points out that meets this red line meets this diamond or circle. And here, by using L2 norm, we can clearly see that the L2 value, theta 2 has a relatively high value, but very small, a relatively small value for theta 1. But in the case of lasso, it is very high probable to meet at some points with this point, where a theta 1 is just exactly the same as 0. So that means we selectively choose a theta 2 as only values. So that's why we have 0 values for theta 1. And because of that, we have some selective features only for the lasso problem. And that's the only difference between the lasso and leech by using L1 norm or L2 norm for measuring the magnitude of the theta value. Summary, we have looked into the problem of overfitting problems. And of course, the fundamental problems of raising the overfitting problem is that the generalization error. So of course, when you add some more features, that will always decrease the loss for training, only for training data. So however, if you keep increasing many features, of course, it will decrease the loss for training, but it is high probable to increase the loss for test data. Then how do we determine when an algorithm achieves good performance? So for that, the first way is divide the data into two parts of training set and test data set. And of course, the amount of value or the amount of percentage depends on what you choose. And in general, it is good to choose 7 or 80% of the data for training and 20 to 30% for test data set. And by training model using training data set, and then after the training is done, you may test your model with test data set, which is actually unseen data for this training this model. So performance on testing set called generalization performance. So you should always check this generalization performance by checking the performance test using test data set. So this is the one way to avoid the overfitting problem, and the second way is just using the fewer features like fewer models or fewer polynomial degrees or fewer RBF function. And the third way is to using the regularization, either both lasso or leech. That's it for today's lecture. Yeah, and Thanks for your listening.